Welcome to our comprehensive guide on semiconductor devices. In this video, we'll explore the essential building blocks of modern electronics: diodes, bipolar junction transistors, BJTs, and field effect transistors, FETs. These components are fundamental to circuits, enabling functions like amplification, switching, and signal shaping. We'll start by understanding how diodes limit voltages, then move through the basics of BJTs, and finally dive into the world of FETs and MOSFETs. Whether you're a student or an enthusiast, this journey will clarify how these devices operate and interact within electronic systems. Let's begin by looking at diode limiters, also known as clippers. Diode limiters, or clippers, are circuits designed to remove portions of a signal voltage above or below certain levels. They're widely used to protect sensitive components from voltage spikes and to shape waveforms in signal processing. There are two basic types: positive limiters, which clip the positive part of the input voltage, and negative limiters, which clip the negative part. By controlling which part of the signal is clipped, these circuits help maintain desired voltage ranges and prevent damage or distortion. Let's examine how a positive diode limiter works in practice. Positive diode limiter, also called a clipper, is designed to restrict the positive part of an input voltage. When the input voltage exceeds a certain threshold, the diode becomes forward biased and conducts, effectively clipping the voltage to that threshold. This is particularly useful in applications where only the negative or zero portions of a signal are needed, or where excessive positive voltages could cause harm. The circuit diagram shows how the diode is positioned to allow only voltages below the set level to pass through. Next, let's look at the negative diode limiter. Negative diode limiter operates in a similar way, but clips the negative part of the input voltage. When the input voltage drops below a certain threshold, the diode conducts, preventing further decrease. This ensures that the output voltage never falls below the set limit, safeguarding circuits from negative voltage spikes. The diagram illustrates the configuration, showing how the diode is oriented to block negative voltages. Understanding both positive and negative limiters is crucial for designing circuits that require precise voltage control. Biased diode limiters add a bias voltage in series with the diode, allowing the clipping level to be adjusted. By changing the bias voltage, you can set the exact point at which the diode starts conducting and clipping the signal. This flexibility is valuable in applications where different voltage thresholds are needed. The circuit diagram shows how the bias voltage is incorporated, and the operation depends on the sum of the bias voltage and the diode's forward voltage. Let's see how this works for both positive and negative biased limiters. In a biased negative limiter, the bias voltage is set so that the diode only conducts when the input voltage drops below a specific negative threshold. This allows for precise control over the minimum output voltage, making it ideal for circuits that require strict lower voltage limits. The diagram demonstrates how the bias voltage and diode work together to achieve this effect. By adjusting the bias, engineers can tailor the limiter to their exact requirements, ensuring reliable operation in various scenarios. Diode clampers are circuits that add a DC level to an AC voltage. They're used to shift the entire waveform up or down, which is essential in signal processing and communication systems. There are two main types: positive clampers and negative clampers. Positive clampers shift the waveform upward, while negative clampers shift it downward. The operation relies on capacitors and diodes working together to charge and discharge during different parts of the AC cycle. Let's look at the positive clamper circuit First, negative clamper circuit operates by shifting the AC waveform downward. During the positive half cycle, the capacitor charges, and the diode controls the voltage level. This results in the entire waveform being moved below the original reference point. Clampers are vital in applications where signal alignment is necessary, such as in television receivers and communication systems. Understanding how clampers work helps in designing circuits that require precise voltage positioning. Transistors are the backbone of amplification in electronics. The basic principle involves transferring resistance from input to output. When the input is forward biased, resistance is low, allowing current to flow easily. The output is reverse biased, resulting in high resistance and a larger voltage. The same current flows through both input and output, but the output voltage is much higher, enabling amplification. This process makes transistors essential for boosting weak signals in audio, radio, and other applications. Bipolar junction transistors, BJTs, are called bipolar because they use both positive and negative charge carriers. There are two main types, NPN and PNP. BJTs have three terminals: base, emitter, and collector. The base is the central part. The emitter initiates electron movement, and the collector gathers electrons. Two PN junctions exist in each transistor, enabling the transfer of resistance from a low resistance input circuit to a high resistance output circuit. This structure is key to their amplification capabilities. BJTs are constructed using either NPN or PNP combinations. In a PNP transistor, two P-type materials sandwich an N-type material, while in an NPN transistor, two N-type materials sandwich a P-type material. The collector is lightly doped, and the emitter is heavily doped, affecting the conductivity of each layer. Higher doping levels result in greater conductivity. This construction determines the transistor's performance and is crucial for understanding how BJTs function in circuits. The constructional features of BJTs are vital for their operation. The collector is lightly doped, while the emitter is heavily doped. The base is sandwiched between these two regions and is lightly doped. Doping levels directly influence the conductivity of each layer, which in turn affects the transistor's efficiency and amplification properties. Understanding these details helps in designing and selecting the right transistor for specific applications. Biasing is essential for the operation of BJTs. Without proper biasing, semiconductor devices cannot function. The main goal of biasing is to reduce the depletion region, allowing current to flow efficiently. Biasing voltages are applied to both input and output terminals, ensuring the transistor operates in the desired region. The diagrams illustrate how biasing affects the depletion region and enables the transistor to amplify signals. Biasing currents are crucial for transistor operation. The input terminal receives base and emitter currents, while the output terminal handles collector current. Proper biasing ensures that the transistor operates efficiently, reducing the depletion region and allowing for effective amplification. The diagrams show how these currents flow through the device, highlighting the importance of biasing in maintaining stable operation. BJT biasing, the input terminal emitter base, is forward biased, thinning the depletion region and allowing majority carriers to flow from emitter to base. The base, being lightly doped, has few majority carriers, resulting in minimal recombination. The output terminal is reverse biased, collecting the majority carriers from the input. This process is essential for the transistor's amplification function, ensuring efficient transfer of charge and signal. The input terminal of a BJT has parameters like base current, emitter current, and base emitter voltage, VBE. The output terminal features collector current, IC, and collector base voltage, VCB. Biasing voltage is applied to both terminals, ensuring proper operation. These parameters are fundamental for understanding how BJTs amplify signals and maintain stability in electronic circuits. BJTs operate in three regions: active, saturation, and cutoff. In the common emitter configuration, the input is base emitter and the output is emitter collector. The characteristics curve shows how the transistor behaves in each region, with equations defining current and voltage relationships. Understanding these curves is essential for designing amplifiers and ensuring reliable performance. In the cutoff region, both input and output terminals are reverse biased, resulting in zero collector current. In the saturation region, both terminals are forward biased, allowing maximum current flow. The active region is where the transistor operates for amplification, maintaining biasing equations. These regions are crucial for understanding how BJTs switch and amplify signals in electronic circuits. The BJT equivalent circuit includes three terminals: base, emitter, and collector. DC currents and voltages are defined for each terminal, such as IB base current, IE emitter current, IC collector current, VBE base emitter voltage, VCB collector base voltage, and VCE collector emitter voltage. These parameters are essential for analyzing and designing transistor circuits. BJTs can be configured in three ways: common base, common emitter, and common collector. Each configuration has unique input and output characteristics, affecting gain and impedance. The common emitter configuration is widely used for amplification, as it provides high gain. Understanding these configurations helps in selecting the right setup for specific circuit requirements. In the common emitter configuration, the emitter is shared between input and output terminals. The input consists of base emitter, and the output consists of collector emitter. This setup is popular for amplification because it offers high gain and good stability. The diagrams show both PNP and NPN configurations, highlighting the common emitter's role in circuit operation. In this configuration, the input current is the base current IB, and the input voltage is VBE. The output current is IC, and the output voltage is VCE. This arrangement allows for efficient amplification, making it a staple in audio and signal processing circuits. The diagrams illustrate how these currents and voltages interact within the common emitter setup. Amplification factor in BJTs is represented by beta-beta. In DC mode, beta is the ratio of collector current, IC, to base current, IB, typically ranging from 50 to over 400. In AC mode, the amplification factor is similar, with slight variations. Understanding beta is crucial for designing amplifiers and predicting transistor behavior in different operating conditions. Biasing also determines the operating point, or quiescent point Q point, of a BJT. The operating point defines the region used for amplification. At point A, the device is off. At point B, the signal varies from the operating point. At point C, there's less variation. Point D sets the device near maximum voltage and power. Operating in a region where gain is constant ensures consistent amplification across the input signal swing. The cutoff region features negligible collector leakage current, with both junctions reverse biased. In the saturation region, increasing base current boosts collector current until saturation is reached, and both junctions are forward biased. The active region is where amplification occurs, with the base emitter junction forward biased and the base collector junction reverse biased. These regions are key to understanding transistor switching and amplification. BJTs act as switches in electronic circuits. In the cutoff region, the base emitter junction is not forward biased, so the transistor is off. In saturation, the base emitter junction is forward biased, and sufficient base current produces maximum collector current, turning the transistor on. These switching operations are fundamental for digital logic and control circuits. The DC load line connects the cutoff and saturation points, illustrating the transistor's operation range. At the bottom, IC is 0 and VCE is maximum cutoff. At the top, IC is maximum and VCE is minimum saturation. The active region lies between these points, where amplification occurs. Understanding the load line helps in designing circuits for optimal performance. Transistors have maximum ratings for power dissipation, defined by the product of VCE and IC. Both cannot be maximum simultaneously. If VCE is at its peak, IC must be calculated accordingly, and vice versa. Exceeding these ratings can damage the device, so understanding and respecting maximum ratings is crucial for safe and reliable circuit design. Junction field effect transistors, JFETs, operate with a reverse-biased PN junction to control current in a channel. They come in N-channel and P-channel types. JFETs have 3 terminals: drain, gate, and source. The structure involves diffusing P-type regions into N-type material to form a channel, with both P-type regions connected to the gate. This configuration allows for precise current control. In JFETs, DC bias voltages are applied to control current flow. VDD provides drain-to-source voltage, while VGG sets the reverse bias voltage between gate and source. Reverse biasing creates a depletion region along the PN junction, increasing channel resistance and restricting width. By varying gate voltage, the channel width and resistance are controlled, thus regulating drain current, ID. Schematic symbols for JFETs represent their structure and operation. Understanding these symbols is essential for reading circuit diagrams and designing electronic systems. The symbols differentiate between N-channel and P-channel devices, helping engineers quickly identify the type and function of each transistor in a circuit. Pinch-off voltage, VP, is the value of VDS, at which ID becomes constant for VGS equals 0V. Increasing VDS above VP produces an almost constant drain current. IDSS is the maximum drain current for a given JFET, specified when VGS equals 0V. These characteristics are vital for understanding JFET operation and designing circuits with stable current flow. When VGS equals 0V, increasing VDD causes ID to rise proportionally between points A and B, known as the ohmic region. At point B, the curve levels off, entering the active region where ID becomes constant. As VDS increases further, the depletion region offsets the increase, keeping ID stable. These regions are crucial for understanding JFET behavior in circuits. Breakdown occurs at point C when ID increases rapidly with further VDS increase. Operating beyond this point can cause irreversible damage. JFETs are always operated below breakdown within the active region. Understanding breakdown is essential for ensuring device longevity and safe circuit operation. Applying a bias voltage, VGG, from gate to source allows control over drain current ID. As VGS becomes more negative, ID decreases due to channel narrowing. Each increase in VGS causes pinch-off at lower VDS values. The amount of drain current is directly controlled by VGS, making JFETs ideal for variable current applications. The cutoff voltage, VGS, off, is the value of VGS that makes ID nearly zero. JFETs must operate between VGS equals 0V and VGS off, with ID ranging from maximum IDSS to almost zero. This range is crucial for controlling current and ensuring proper device operation. Maximum current in FETs is defined as IDSS, occurring when VGS equals 0V and VDS greater than VP. For VGS below the pinch-off level, drain current is zero. For VGS between 0V and pinch-off, ID ranges between IDSS and zero. These characteristics are similar for P-channel JFETs, providing flexibility in current control. The relationship between ID and VGS in FETs is defined by Shockley's equation. When VGS equals 0V, ID equals IDSS. At VGS equals VP, ID equals 0. The transfer curve illustrates how drain current varies with gate voltage, helping engineers design circuits with precise current control. MOSFETs, metal oxide semiconductor field effect transistors, are another category of FETs. Unlike JFETs, MOSFETs have no PN junction. The gate is insulated from the channel by a silicon dioxide layer. There are two main types, enhancement E and depletion D. Enhancement MOSFETs are more widely used, and polycrystalline silicon is often used for the gate material. These devices are sometimes called IGFETs, insulated gate FETs. MOSFETs operate only in enhancement mode and lack a structural channel. For N-channel devices, a positive gate voltage above a threshold induces a channel by creating a thin layer of negative charges. Increasing gate-to-source voltage enhances channel conductivity. Below the threshold, no channel exists. This operation is fundamental for digital and analog applications. MOSFETs can operate in depletion or enhancement mode. The drain and source are connected by a channel adjacent to the insulated gate. A negative gate voltage depletes the channel of electrons, reducing conductivity. A positive gate voltage enhances conductivity. This dual-mode operation provides flexibility for various circuit applications. In depletion mode, a negative gate voltage repels conduction electrons, depleting the channel and decreasing conductivity. At sufficiently negative voltage, the channel is fully depleted and drain current is zero. In enhancement mode, a positive gate voltage attracts more electrons, increasing conductivity. These modes are essential for designing versatile electronic circuits. MOSFET schematic symbols distinguish between eMOSFET and DMOSFET types. Recognizing these symbols is important for circuit design and troubleshooting. The symbols indicate the device's mode of operation and help engineers quickly identify the correct MOSFET for their application. LDMOSFETs and VMOSFETs are advanced MOSFET types designed for power applications. LDMOSFETs have a lateral channel structure, allowing higher current and voltage. VMOSFETs use a vertical channel structure for higher power capability and improved frequency response. Dual-gate MOSFETs reduce input capacitance, making them suitable for high-frequency RF amplifiers and automatic gain control. Depletion and enhancement MOSFETs have distinct transfer curves and characteristics. For depletion types, ID equals IDSS when VGS equals 0V, and ID equals 0 at VGS equals VP. Enhancement types require VGS above threshold for current flow. FET amplifiers use these devices for high input resistance and voltage gain. Understanding these characteristics is key for designing efficient amplifiers and signal processing circuits. FET amplifiers use AC models with internal resistance between source and gate, and a current source equal to GM VGS between drain and source. The resistance is assumed to be very large, creating an open circuit between gate and source. The voltage gain is calculated as AV equals GM/RD. These models are essential for designing amplifiers with high input resistance and efficient voltage gain. Common source jfet amplifier applies the AC input signal to the gate and takes the output from the drain. The source terminal is common to both input and output. The input voltage causes gate to source voltage to swing, resulting in corresponding drain current changes. As drain current increases, voltage drop across RD increases, causing drain voltage to decrease. The drain to source voltage swings are 180 degrees out of phase with gate to source voltage. The transfer characteristic curve of a jfet shows how the signal operates. The input signal causes gate to source voltage to swing above and below its Q point, resulting in drain current swings. This operation is fundamental for amplifying signals in audio and communication circuits, providing stable and predictable performance. Mosfet amplifiers. The signal voltage causes VGS to swing above and below zero. Producing swings in ID positive VGS induces enhancement mode, increasing ID, while negative VGS induces depletion mode. Decreasing ID. The DC analysis is simpler than for JFETs, as ID equals IDSS at VGS equals 0. This operation is ideal for amplifying signals with variable gain. Common source N-channel MOSFET amplifier uses voltage divider bias with an AC source coupled to the gate. The gate is biased with a positive voltage above threshold, and the signal voltage causes VGS to swing around its Q point. This operation is fundamental for amplifying signals in digital and analog circuits, providing high gain and stability.